Hi everyone. So I think you're all here, so we'll get started. Let me just start with a couple reminders. So the first one, it's about homework night due tonight at 11:55. Okay, so if you haven't submitted your work, make sure you submit by 15 or 11:55. Okay. Um, so the second announcement or reminder is exam 3 will be on Wednesday next week after you come back from the break. Okay, so that's on exam 3. I have set up let me show you the on the Moodle page here. Okay, so on the Moodle page of the class, I have set up the this here exam 3. Okay, so this is what you see if you just join in or just click get into the page. So you want to click on show more here. So then there's this exam 3 setup, okay, for you guys to submit your exam 3 work next week on Wednesday. Okay, so about at 12:30 I'll be sending you guys your exam. Okay, so each of you guys will get a different version of the exam. So then you have about 2 hours to finish your exam, okay? So you want to submit over here, right? Now, for the other class, I had this today earlier when I set up exam 3. So most of them were able to submit the exam on Moodle, but some of them was having difficulty, like they, I don't know what happened, but they said a couple of them said the Moodle wouldn't let them do that. So I don't know what actually went on wrong on those two scenarios, but try that next week. Okay, so if you couldn't submit your work on Moodle, then you can submit in email. Okay, so so if you are doing the in email, I again would prefer PDF file. Okay. On exam 3, so it will cover chapter 15 and 16, okay? And then if you want to study the homeworks, it's homework 7 through 9, okay? 7, 8, 9, all right? Any questions you guys have on exam 3?
Yeah, how many questions is it?
So it'll be either 5 or 6, okay? So yeah, so some of you guys may have 5, but some of you may have 6, but yeah, if you get 6, then there will be 2 of them are shorter one, like 10 points each. Okay, if you are getting 5, then they are like kind of relative long questions, like 20 points each. Okay.
Is it just going to be the same like format as the other tests that we've been given?
Yeah, pretty much the same, but again, you'll be having open book format. Okay, so you can check whatever, like yeah, textbook or whatever notes, okay, or whatever online. Okay.
Okay.
Yep.
Okay, thank you.
All right. Other questions you guys might have? So if not, then we'll get started on the lecture part. Okay. So today we'll be checking section 2 and 3 of chapter 17 here. All right. So today's objectives are here. So apply the 3 equations of motion for a rigid body in the plane of motion, and then analyze problems involving translational motion only. Okay, so today we'll be just looking for problems with translational motion, and then later on we'll be looking at rotational motion as well. But that's all we will be doing today. So usual stuff items here. All right, so that's again get started with the reading quiz. Okay, so today's reading quiz will be also for extra credits. Okay, so send me your answers in the chat privately. I think most of you guys have some of your responses, so we'll kind of close out the quiz and move on here. So let's take a look on the first one. It says when a rigid body undergoes translational motion due to external forces, the translational equation of motion can be expressed for. So then you can apply translational equation of motion to, actually we can do it on the center of mass. Okay, so this one will be B. Okay, and then the second one here, it says rotational equation of motion, EOM means equation of motion about the mass center of the rigid body indicates that the sum of moments due to the external loads equals to, okay, so moments should be equal to moment of inertia times angular acceleration. So IG times alpha, okay, so that should be the correct answer for the second one. Okay, so B and A on the reading quizzes. Okay. All right. So, so a lot of cases when an object is moving, it could have translational motion, or it could have at the same time have rotational motion. Okay, depending on where the forces are applied. Okay, so in this case, you will see like for the trailer, there's a bolt on it. Okay, so then the bolt and trailer is in translational motion. Okay, now for a tractor like this, if it picks up some loads, okay, so then for the loads, okay, it kind of also having a translational motion in this case. So it's curvilinear translational motion, okay, and then that's what we want. We don't want the load to be slipping and then falling off the ground, okay. So that's what we wanted, and then we should be looking at all different forces on the load and then see how that is can be maintained. Okay, so that's the topic of the day here. Okay, so imagine if you have an object. Okay, so this guy here in the figure. So there, if there are several forces on the object, okay, so then you can see for because the forces are acting on the object at different locations, so there's possibility that this guy might be rotating due to all these forces. Okay, so you can look at the net force coming from these four forces. You can also look at the net moment, okay, coming from those four forces, okay, or we call it torque, okay. So each force will exert a torque about one axis, okay. Then we can take a look at that as well, okay. So net force and then net torque, that's what we are looking at, okay. So if there's net torque, then the object will be rotating, having rotational acceleration. If there's net force, then the object will have acceleration. Okay? So if we are just considering a translational motion, so then we can use the equation of motion for translational motion, which basically says net force on the object should be equal to the mass times the acceleration, okay, on its center of mass. Okay, so A sub G, G means center of mass or center of gravity. Okay? So then if this is a planar motion, you can have the motion either in x direction or in y direction. So there's two components. So the scalar form will be the x component of it, net force equal to mass times acceleration on the center of mass. Okay, and then the y component force should be equal to mass times the y component of the acceleration on the center of mass. Okay, and then the net force equal to mg, that's the vector form. Okay, so vector form can be resolved into x and y components. Okay, and then because we have planar motion here, so it only focuses on the plane of x and y. Okay, you can always choose the x, y to be on the plane of the motion. Okay, so then you always have x motion, equation of motion, and then y equation of motion in that way. Okay. So the sum of all external forces acting on the body should be equal to the body's mass times the acceleration, which is basically Newton's second law. Okay. Now, if there are multiple forces, okay, or if there are external forces on the body, then we also need to consider the moments of those external forces, okay, or the torque of it. Okay, so in this case, then if we are looking at the total moment, okay, so it'll be coming from torque of the external forces and then the moment exerted on the system, if there's moment exerted on the system, okay, by say by motor, okay, so then this is all you have, okay, so Ri cross Fi, okay, will give you the torque by the forces on the ice object, okay, in summing overall all the objects of the system, if you have a system of multiple objects, okay, or sometimes you have objects that have different parts, okay, then you can still denote each part as the ice part, okay, then you can do that as well. All right, now for the force, you can also write as mass times A sub G, okay, and then this would be the average R, okay, and then plus, okay, IG alpha, okay, so then now there's a great deal of derivation in the textbook, okay, you guys should read through them, but I found it's kind of difficult maybe for you guys to understand, but at the end, it sums up that this guy, the moment about a point P should be equal to the connecting moment of each point, okay, and then you sum it up, okay, so this equation is basically coming from here, the kinetic diagram here, so one, this is the total moment, okay, from the four forces, and then this is from the kinetic diagram over here. So basically coming from the yeah, over here. So that's what you have here. Okay, so yeah, don't worry about too much about this. Okay, so when we talk about the examples, you'll see actually, although it looks like derivation is hard to follow, but at the end, when you are applying these equations, they're actually much simpler than you might have think. Okay, than you might have thought. So because this is a planar motion, so again, the vectors, okay, for the position vector, it should have an x component, y component, or ing. Okay, so that's what you want to keep in mind. All right. Now, in the case of, okay, if the point of point P, so that's the point where the x rotation is going through, if that coincides with the mass center, okay, then the equation reduces to moment of, okay, summation of all the moments should be equal to the moment of inertia through the exit, about an exit going through the center of mass times alpha angular acceleration. Okay, so basically over here, okay, so then this, okay, okay, so this will go away, and then this will go away. Okay, so then you'll have this guy equals to that guy. All right. All right. Now, the three equations you might be using is this one. So from the net force equal to mass times acceleration, x and y component. Okay, so those are two equations. And then the last one will be either this guy or this guy. Okay, if you have the rotational axis through the center of mass, then you have this equation. If you are having it through a point P, okay, then you have this equation. Okay, from the connected diagram there. Okay, so then simply these are the equations you are using. Okay, so for today's examples, we are pretty much focusing on those three equations. Okay. All right. So for the simplest case, if we consider only translational motion, okay, then alpha should be equal to 0. Okay, so then there should be no rotational acceleration. Okay, then Ag is equal to the acceleration of the object. Okay, that should be the same because there's only translational motion. So every point on the object should share the same acceleration. Okay, so then if that's the case, if there's no rotational, then this equation becomes 0 because I times alpha then becomes 0. Okay, and then the two equations for the net force, okay, Newton's law still applies in the x direction and in the y direction. Okay. Now, if you have an exit that is not through the center of mass. So for example, point A here. So if it's not rotating with the object is not rotating with point G, the center of mass, if it's rotating about this point A other than G, okay, so then the moment, summation of moment, okay, about this new axis A should be equal to whatever you have from here plus mga times d, okay. So this is the net force times the d, okay, would be the distance over here from here to there, okay, the perpendicular distance over there, okay, so this mg, okay. All right. So if a rigid body is subject to a curvilinear translation, okay, so if it having curvature motion like that, okay, so then it's most convenient to use a normal and tangential coordinate system, okay, so N and T, you can apply that. So if you are using an N and T coordinate system, okay, then again, the net force in the normal direction should be equal to m times the oscillation in the normal direction, and then normal force, net force in translational motion should be equal to mass times oscillation in the translational direction, okay. And you could either have net moment equal to 0, okay, if that's your x rotation, okay. If it happens to be through the center of the mass, then this is a curvilinear translation. There's no rotational motion on the object, okay, so that's equal to 0, okay. Or if sometimes you are looking at a different x rotation, say point B here, okay, then this is where the net force will be exerting, okay. Then if that's your x rotation, then there will be a net moment, okay, because simply because you are choosing a different x rotation, all right. So then in that case, you can see this is what it will have, okay. So for a moment, this is what a moment should look like, okay. So although there's no detailed derivation, but I can show you quickly on this one here. So for moment, net moment about rotational xb, this should be coming from the r cross the net force, okay. So then r, now you are having a new x rotation, so it will be r of center of mass with respect to this new point, okay. So in the coordinate system like this over here, in the tangential direction and the normal direction, if that's the one we are using here, and then point B is somewhere over here. So this point B, it's H. In the tangential direction is E in the normal direction, okay? So then R of G with respect to B should be equal to, let me see, this should be equal to E in the normal direction, okay, plus H in the tangential direction, okay, in the vectors cross, okay, the net force. Net force you can write as mass times oscillation G, okay, in the tangential direction plus in the normal direction, okay. Let's do it that way, okay. So then this is AG sub T in the T direction plus AG sub T in the normal direction, okay. So if you do cross product here, okay, then this is what this guy is about, okay. So it turns out to be E times M AG in the tangential direction, okay, minus H, okay, M A G in the normal direction, okay. So because cross product of, if you are doing T cross T unit vector, that goes away, okay, it becomes 0 if you are doing N cross N goes away. So at the end you will just have two terms remaining, which is the En cross this guy, okay. So this cross this plus this guy cross this guy, okay. But So if you are doing n cross t, it gives you positive, and if you are doing t cross n, it will give you negative. Okay, so that's the negative sign. All right. So that's the magnitude. Okay, so that's why where this equation is from. Okay, the last one on the slides here. Okay. All right. So procedures to take for solving problems. So the first is to establish either x, y coordinate or an n and t coordinate. Okay, so if you have a curved linear motion, you'll use an nt coordinate system. That's most convenient. Okay, otherwise you can use an xy. Okay. The second one is to draw a free body diagram, and then also the kinetic diagram showing all the external forces. Okay, then you can set up the translational equation of motions. Okay, and then you can indicate also the couple of moments and the initial forces and couples on your diagram. Okay, and then the third one is identify the unknowns and then apply those equations. Okay, so you're either going to have this 2 plus this guy or plus this guy. Okay, this is in the xy coordinates. Okay, this one it's in the nt coordinates. Okay, normal and tangential direction coordinates. Okay, so either way. All right. And then if there's friction forces involved, so remember friction forces always acts on the body, opposing the motion of the body. Okay, so if you know the direction of motion, then the friction force will be in the opposite direction. Okay. All right, so let's take a look. Concept quizzes here. There are 2 of them here, one here, and then one on the next slide. Okay, so if you have your PowerPoint slides open, you can check on those 2 quizzes. But I'm going to open the breakout rooms for you guys to work together. Okay, so 4 rooms, and then automatically assign participants. Okay, so I have them open now. You can join them. All right, so I think you're all back, and then I see responses from at least each of the breakout rooms. So yeah, so the first one here, we are looking for the free body diagram of the system here. Okay, so as the disk is rolling to the left, okay, so then I think one force to take is the friction force. Okay, that will give us the easier picture over here. So the friction force should be to the right. Okay, and then in this case, because it's static friction, because it's rolling without lifting, that means static friction. Okay, so then it's to the right. Okay, so it should be C. Okay, on this one. On A, it doesn't have the right direction for the friction force. On B, there's no friction force. Okay, so C should be the only correct one. Okay, and then all the other forces on the system they are indicate correctly. Okay, as well. All right, so that's the first one. And then the second one here, now this time if the disk is rolling with slipping, okay, so that means there's a relative motion between the disk, the contact point of disk, and then the floor over here. So then in this case, again, the disk is going to the left, so friction force should be to the right, okay? So we should be looking for the friction force to the right, okay? So then A is not right, okay? So this is the one here, okay? It's the kinetic friction. So B looks like has the right notation Fk, okay, but it doesn't include the weight on the disk itself. Okay, it puts all the weight on the rod here, so that's not right. Okay, so C on the second one as well. Okay, so C and C, right, and then all the responses are C and C. So you guys did a very good job on this one. Okay. All right, so let's take a look a couple of examples, and then at the end, if we have time, we can look on the group problem solving. Okay, so the first example here, given the picture here, there's 100 newtons of force on the handle, and then there's the front wheels, the back wheels, okay, A and B, and there's center of mass of the car itself. Okay, so so let's see, and then the geometries are indicated. Okay, so the distances from each point to the center of mass are indicated. Okay, so we are not looking for normal reactions at each of the two wheels at A and B. Okay, so then we can say the front wheel A here, that is normal force of A, and then on the B here is normal force of B. Okay, so then we are looking for NA and NB. Okay, so pretty much we will be just following the procedures a couple of slides ago. Okay, so the first thing to do is to set up a coordinate system. Okay, X and Y. Okay, the second thing to do is draw the free body diagrams. Okay, so indicating all the forces. So NA here, NA, NB here, and then this is the weight, okay, on the cart, and then this is the external force, okay, applied force, right? And then this is the kinetic diagram, okay. So overall net force should be equal to less m times ag, okay, in the x direction, because there's no motion in y direction, so we only have that component. Okay, all right, so then we can apply equation of motions in the x direction. Okay, so net force in the x direction, this guy you can resolve into two components. All right, so in the x component, it's going to be 100 times 4 over 5. Okay, so that's this guy here. All right, that's the cosine of the angle there. Okay, so that should equal to, okay, because all the other forces are vertical direction. Okay, so the x component of this force should be the net force in the x direction for the car. Okay, so times 100 times ag, the acceleration of the car. Okay, so that will tell you the acceleration of the car is 0.8 meters per second squared. Okay. All right. So once we have that, we can apply. So the second equation is the equation of motion in the y direction. Okay. So in y direction, there's no motion. So that means net force should sum up to be 0. Now these two forces, the normal reactions are in the positive y direction. The weight is in the negative y direction, and then this force pushing it down. So the y component of this force should be also negative. Okay. So then you will set up this way. So NA plus NB minus the weight minus this force equal to 0. Okay. You have two unknowns here. You only have one equation, so you need a second equation. Okay. So because the system is just having translational motion, there's no rotational motion. So then the net moment about the center of mass should be equal to 0. Okay. So then you can set it up in this way. So net moment of initial, okay, or net moments of all the forces. Okay. So on A here, because if you look at this point here, so this is the choose the center of mass to be your rotational axis. Okay. So then on A point, normal force on A point should make it rotate counterclockwise. Okay, so that's positive. So usually we take counterclockwise our rotation to be positive. Okay, and then clockwise rotational to be the negative direction. So NA should give you a positive torque. NB will give you a negative torque because it's going to make the system rotate about the G in the clockwise direction. All right. Now this guy here, the y component of this force, okay, so you can take the y component, it's pointing downward, it has distance of 0.3 plus 0.7 to be, or 0.3 plus 0.4 to be 0.7, okay, so then the force times r, okay, that give you torque. This will make the system go in the counterclockwise direction, so positive, all right. Now the x component of this force will be pointing in that direction, and then we will give the system rotate clockwise direction, so negative. Okay, negative 100 times 4 over 5, that's the x component, times the distance to the center to the x rotation would be 1.2 minus 0.5, that would be the y. Okay, that goes to 0 because the system as a whole doesn't rotate. Okay, so then you have two equations. Okay, 1 and 2 with two unknowns. All right, so you can solve for the two unknowns from these two equations. Okay, so solving for equation 1 and 2 gives you NA to be 430 and then NB to be 611 newtons. Okay, and then these are what you're looking for. Okay, so you realize that probably at this point that the x direction equation of motion actually, if you don't do it, that doesn't matter, right? Because for the y equation of motion plus this net torque equal to 0 or net moment equal to 0, then you'll be able to solve for the two unknowns. Okay. All right. Any questions you guys might have? Okay, so if you are good, then we are going to check on example 2 here. Okay, so example 2 here, it says the 100 kilogram table has a mass center at G, and the coefficient of static friction between the legs of the table and the bed of the truck is 0.2. All right, so there's a desk on the bed of the truck here. Okay. And then it's asking you to find the maximum oscillation of the truck possible without causing the table to move relative to the truck. Okay. And then the corresponding normal reactions, legs A and B. Okay. So again, we'll be following the procedures for the analysis here. Okay. So this guy, the table is sitting on a bed over here, okay, without relative motion to the track. Okay. So if the track will have oscillation A, that means the table will also have oscillation A. Okay. So it will be the maximum oscillation, so the two doesn't have relative motion. with respect to each other, and then will be NA and MB. Okay, so in this case, you can see I'm looking for three unknowns. You're looking for oscillation, okay, and then NA and MB. So three unknowns. You probably realize that you need three equations in here. Okay. All right, but first, okay, so we'll look at the free body diagram here. Of course, before this, we should set up a XY coordinate system. Okay, so we can take X to be the horizontal to the right, Y to be vertically upward. Okay, so that's the normal X and Y coordinate system we would have. Okay, so then the free body diagram over here on the table, on the desk over here. So you'll see a weight, okay, on it, and then you'll see normal reactions A and B, so normal forces at point A point and then B point. And then there should be friction force. Okay, so if the desk and the track bed doesn't have relative motion, then we are looking at the static friction. Okay, so static friction on B and then static friction on A. So normal force on A and normal force on B, they don't necessarily would equal to each other. So that means the friction force on A and the friction on B doesn't necessarily have to be the same. Okay, in the previous case, we see that on the cart, on the two wheels, the normal forces are different. Okay, so in this case, it might be well the case as well. Okay, but we'll take a look here. So this is your free body diagram. This is your kinetic diagram. So it has oscillation, okay, to the x direction. Again, in the y direction, there's no motion here. Okay, so so you really have just three unknowns, so NA, NB, and then AG. Okay, because FA and FB, although they are two unknowns, but they are in terms of NA and NB. Okay, so then you only have three unknowns. Okay. All right. So then we'll apply equation of motions in x direction, and then we'll apply equation of motion in y direction. All right. And then we should have a third equation on the net moment, okay, on net torque for each of the forces to be 0. Okay. So in the x direction, the net force should be coming from the two frictional force. Okay, so mu times NA plus mu times NB. Okay, mu is 0.2. Okay, they're both 0.2. That should equal to m times A. Okay. In y direction, the net force should be 0. So this y direction, the weight should equal to NA plus NB. Okay, or NA plus NB minus the weight should go to 0. Okay, so two equations, and then the third equation over here. So the third equation comes from the net torque from each forces should sum up to be 0. So the net moment should be 0. Okay. So on this guy here, so on this force FA, friction force on A point, okay, so that's again 0.2 times the normal force times 0.75, that's its distance to the x rotation at point G, okay, again, this will make it rotate counterclockwise, okay, plus 0.2, okay, times this guy times MB, that's this friction force, will again make this rotate counterclockwise, okay, times 0.75, that's the distance there again. Now plus NA, okay, times 0.9, so this is NA over here, perpendicular distance to the x rotation will be 0.9, all right, it's making it rotating counterclockwise, so it's positive, but NB, okay, will make the x rotate clockwise, okay, so NB times 0.6, so that goes to 0, okay, so you have three equations with the three unknowns set up now, and then you can solve for it, okay. All right. You realize that in equation 2 and 3, there's just NA and NB as unknown, so you probably can use those two equations first. Then you can solve for NA and NB. Okay. So solving equation 2 and 3 at the same time, you have your normal reactions at point A and point B. With that, you can have your oscillation. Okay. So the maximum oscillation of the central mass to be that. Okay, take A and B into equation 1. You'll solve your H. Okay. All right. Do you have any questions on this one? Um, so if not, then we are going to look at group problem solving. Okay. So we have about 11 minutes now. So I'm going to ask you to join the breakout room again, and you guys can work as groups, okay? And then in about 5 minutes, we'll come back and I'll briefly show you how to solve this together, okay? So join the breakout rooms, and then we'll take a look on the solution in about 5 minutes, okay? right, so I have you guys back here. So I have shown the solutions on the paper here briefly, but again, I'll post the full solutions later on the PowerPoint slide. Okay. So basically, you're going to do an X and Y coordinate system. In this case, because this pulling force is to the left, so I can choose to the left to be X positive. Okay, so it's arbitrary, and then upward to be the Y positive. So basically, you can have three equations reaching here. So X component of net force equal to mass times the X component of acceleration, and then Y component of net force equal to mass times Y component of the acceleration. Okay, in the Y component, acceleration should be 0, and then this is something we can solve for. Okay, the X component of acceleration. So the X component of P force should be 300 cosine of 30 equals to that guy, the mass times acceleration in X component. The Y component, net force. So you have two normal reactions plus the Y component of this P force. Okay, so P sine minus the weight, that should go to 0 because Y component acceleration should be equal to 0. All right. Now, net moment, the system should also be equal to 0 because it only has translational motion, not rotational. Okay. So then you can take the torque by each of these two forces and then this force, okay, the X and Y component of it. That should go to 0. Okay. X rotation going through the center of mass, so the weight wouldn't have any contribution to the moment of inertia. Okay. But basically you set that to be 0. Okay, so 0.2, okay, that's the distance from X rotation G to this MA, okay, and then 0.3 times NA, the last term here, that is in the clockwise direction, so negative, okay, so positive on this guy, right, and then you're going to have positive on the X component of this guy, but the negative of Y component, okay, from that guy. Okay, so two positive, two negatives. Okay, then if you look at just equation 2 and 3, the last two, okay, you can have two equations with NA and NB as unknowns. You can solve for them. Okay, so if I did this correctly, it turned out to be 169 to 69 for the two. Okay, now the problem didn't ask for a x, but you can calculate what's that. Okay, so that's the solution for this one. Okay, any questions you guys may have? All right, so
Dr. O,
yes.
for that, is that 30 supposed to be 300 or is that supposed to be 30 times 30 cosine?
Yeah, that's 0.1 here. So I just multiply 300 by 0.1 to be 30.
Oh, okay.
But yeah.
All right, thanks.
All right. All right, so we'll stop here for today. I wish everyone have a good break. Happy Easter, and then when you guys coming back on Wednesday, you will receive an email from me about at 12:30 on the exam. Okay, you'll click on that link to download your exam. Okay, and then try to turn it in on Moodle. Okay, if you couldn't, then send me that in email, preferably in PDF form. Okay, so see you guys.
Bye. Have a good Easter.
Bye.
See you, Dr. Ho.
All right.